Hello everybody. I wanted to let you know that today what we'll be covering is a probability theory, random variables, and this will be a three-part series of probability theory. The first one will be random variables. The second one will be transformations of random variables, and third one will be sums of random variables. Okay, and you need to know all of these things for inferential statistics, which we'll do after this probability theory and this particular random variables things. Okay, so this is part one as an introduction, just to tell you what random variables are, a little bit about probability, discrete and continuous random variables. In the book, if you look in the book in the appendix, these should be chapters 4, 5, and 6, if I'm not mistaken. Okay, but a lot of this information is not in the book. In this particular chapter, a lot of it is in the book, but with later parts 2 and 3 of these random variables, sums in random variables and transformations of random variables, it's not going to be in the book that much. Okay, anyways, this should be all in the book. Some maybe, some maybe not, but just follow this for now. Okay, so let's start the slideshow. Okay, so what are the goals here? So for now, today's lesson, we'll talk about random variables. We'll talk about what probability is, special distribution families, differences between continuous and discrete random variables, be able to compute probabilities for discrete random variables and continuous random variables. And what are continuous random variables? They're with straight lines, especially. Sometimes they have not straight lines, but we'll try to compute probabilities with straight lines, like the uniform distribution. Okay, and expected value and variance of random variables, or some people say expected value and variance of distributions. Okay. Okay, so what are these? Know how to compute them given any discrete random variable, and know how to compute given formulas for special continuous random variables like the uniform or the normal distribution. Okay, so far we have studied data, how to graph data, how to provide summaries of data using measures of location and variability, in particular the expected value and variance of data, or the mean or the average of and the variance of data, right? Okay, so the goals here, and I'll talk about probability distributions in general, okay, and random variables. So let's have some definitions. What is a probability? Now, the last time in class, we did a poll. I asked you guys, have you seen the statistics before? Blah, 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 blah. So I assume you know what probability means. It's like percentage chance of occurrence. For example, tomorrow I go to the store. What is the chance of me getting coronavirus? I don't know. Maybe 1 in 1,000 or 1 in 10,000, right? To get coronavirus from the store. So this is probability. Or some people say the percentage chance is a 1% chance or 0.5% chance that you will get it when you go to the store tomorrow, okay, or today, okay. So there's always risks, right? Okay. Anyways, probability gives the likelihood that a possible outcome will occur. Therefore, it is analogous to the percent chance of a possible outcome. Okay. The difference between probability and percent chance is that probability is measured between 0 and 1, Well, percent chance is between 0% and 100%. In statistics, if you want to talk more formally, use the word probability instead of percent chance. So in statistics, we use probability, okay, in general. So, for example, if I flip a coin that's a fair coin, like 100 tenge coin or something like this, I flip it, there's a 50% chance it will be heads, or it will land on one side, and 50% chance on it will land tails. Or the probability of landing heads is 0.5, and the probability of landing heads of tails is 0.5. Okay, that makes sense, right? Okay. Okay, then a probability distribution can be thought of as a function providing a probability of occurrence for each possible outcome of an experiment. The probabilities in a probability distribution have to add up to 1, just so you know. So, for example, in a coin flip, you can either have heads and tails, and the probabilities is 0.5 on heads, 0.5 on tails, so these 0.5 plus 0.5, they add up to 1. Okay? All the probabilities in the probability distribution have to add up to 1. Okay? 1, it means 100% chance of occurrence for all possibilities, in a sense, okay? Or probability of 1 of occurrence for everything. This is what it's saying, okay? Okay? Because I know when I flip a coin, it has to land on heads or tails. So it's a 100% chance that it will land on one of those two, all right? Okay? Okay. Okay, everybody. The next thing I'm going to talk about is called a random variable. A random variable can be seen as a variable which has a probability distribution associated with each one of its possible outcomes. So the random variable, you can say the coin flip as a random variable, can be seen as having two parts: a possible outcome, heads or tails, and associated probabilities, 0.5 on each. The possible outcomes are known as the outcome space or the sample space. Sometimes the words probability distribution and random variable are used interchangeably. Okay, some people say a random variable, some people say probability distribution. If you want to be more formal, you technically are supposed to say the random variable has a probability distribution. Okay, in a sense. Okay, so more formal, this is how you say it, more formal. Okay, now more about random variables. They can be what are called discrete or continuous. A discrete random variable is a random variable that has a finite number of possible outcomes. Okay? Each outcome has a positive probability associated with it. The probability distribution associated with a discrete random variable is known as the probability mass function. Okay? And here is an example. Just like we talked about flipping 100 tenge coin or something like this, just a coin flip. A coin flip can be seen as being represented by a random variable called, and you're supposed to name it usually with a letter. So name the coin flip random variable Y. Okay. Then the outcome space of the coin flip is heads or tails. But formally, a random variable requires a numerical outcome space. So let heads represent the number 5. Okay, just 5. And tails represent 10. Why 5 and 10? Just numbers I chose. It could be any number. It could be 0 or 1. Or it could be 100 and 200. or 100 and 101. It doesn't matter, okay? But generally, because it's the outcome space, it has to be a numerical number that represents either heads or tails in general, okay? Then, watch. For the random variable y, which is the coin flip, the outcome space is 5, 10, and the PMF, or the probability mass function, you say probability, like this, y equals 5 equals a half. And probability y equals 10 equals a half. And probability 0 otherwise. So if y doesn't take on the values 5 and 10, or if it doesn't take on the values, the letters, it doesn't take on heads or tails, in a sense, it's 0 otherwise because there's no other options. It has to be either heads or tails. Okay, unless the coin somehow lands on its side, which is not going to happen probably, okay? That's why I said 0 probability for everything else, okay? So this states that if I do the experiment, there's a half a chance that I'll be getting a 5, which is heads in this case, and a half a chance that I'll be getting a 10, okay? And if I flip the coin. Okay. Graphically, how would you graph this coin flip? So the graphical representation on the x-axis here, you're going to put 5, and you're going to put 0.5 to represent a 0.5 probability of landing on heads, on the number 5. And 10 is represented by tails again, and 0.5 that is going to land on tails. Okay? Okay, so this is the coin flip. Another example. Suppose instead of a coin, I roll a die. A die. You guys know what a die is, right? A die has 6 sides and has the numbers 1 through 6 on the die. Okay? So now I have numbers instead of heads and tails, so there's no need to represent other numbers with those numbers. And I can do that also, but it's unnecessary in this case, right? Okay, so let a fair die roll be represented by a random variable. Call this random variable x. The outcome space of the random variable is the numbers 1 through 6. Okay. So again, there's my 6-sided die roll. Okay. And the probability mass function, the PMF, associated with the random variable is the probability value 1/6 for all the numbers 1 through 6. Okay. If I am to roll the die, there is a 1/6 probability, 17% chance to land on any one of the die numbers. In statistics, this PMF is formally written as probability that x equals little x, or any x, okay, is 1/6 for x in 1, 2, 3, 4, 5, 6. So little x can take on any of those values, okay? And 0 for all other x. This is saying the probability of the random variable x is equal to the particular value of x, 1/6 for all possible outcomes, okay? So probability x equals 5 is 1/6, says the probability that the random variable x is 5 is 1/6, for example, okay? Okay. So this is very similar as the coin flip, but we can see here the outcome space are just the numbers associated with the die, 1 through 6, and each one of them will have a probability of 0.17, roughly, of occurrence, okay? I can get a 2 with a 0.17 probability, a 4 with 0.17 probability. Here x, this is the random variable x. That means the random variable in this case is the die roll. Okay, now I'm assuming it's a fair die. a fair die. Okay. Okay. Let's move on. A continuous random variable. A continuous random variable has an infinite number of possible outcomes. Okay. As there are an infinite number of possibilities that the random variable could take, the probability of an exact outcome is essentially 0. So now we're talking about continuous random variables. Before, the coin flip and the die rolls were discrete random variables. Okay. Let's read on. The distribution associated with the continuous random variable is called the probability density function, and it gives probabilities of an interval of values rather than a particular value. Okay. The probability of an interval is given by the area under the curve. The area underneath the curve therefore has to add to the total probability of 1. The PDF does have a functional form, but essentially the values of the output of the PDF are probabilities per 1 unit of x. Okay. Okay. The simplest continuous random variable is called the uniform random variable. Given an interval for possible outcomes, the uniform distribution states that any length subintervals will be equally likely. Okay. If a random variable x is distributed uniformly from a possible outcome space between 2 and 10, then the PDF is given as f of x is 1/8 for x between 2 and 10. In other words, there is only a 1/8 chance for any subinterval of length 1. Okay. So the PDF formula in this case is 1 divided by the length 8. Also specify the location of x. So I'll give you an example here. This is how the random variable might look like. If I tell you x is distributed uniformly between 2 and 10, that means it can take on any value between 2 and 10. Okay. And all intervals of equal length between 2 and 10 are equally likely. That means if I get a number between 9 and 10, it's just as likely between getting a number between 2 and 3. And the chance of getting this is 1/8. Okay, everybody? How did I find out it's 1/8? Well, the total probability, that means getting a number between 2 and 10, has to be 1. Since the length of the base between 2 and 10 is 8 units long, I multiply base times height. Okay, that has to be 1. So so my height has to be 1/8 in order for the area to be 1. Okay. Okay. So another one, get a number between 5 and 6 is 1/8 chance. That means get a number between 5 and 7 is 2/8 chance, 2/8 or 1/4. This is the same as getting probability getting a number between 8 and 10. Also 2/8 chance or 1/4 chance. Okay. Getting a number between, in this case, between, let's say, 2 and 6. Where do you think that the center is here? It's around 6. So getting a number between 2 and 6 is a 50% chance, or 0.5. Okay. So now you understand what a uniform means. What is the probability of getting exactly 6? Exactly 6. It's essentially 0, because getting an exact number, there is an infinite amount of numbers between 2 and 10. An infinite, right? I can get 6 point, because it's continuous, they're not integers here. I can get a number like 6.005. is another number. I can get 6.0056. It's another number, right? So there's an infinite amount of numbers here. So if I say what is the probability of getting a 10, it's 0. What is the probability of getting 5.6? 0. What is the probability of getting 2? 0. So getting the probability of individual numbers is 0, this probability, okay? So this is a continuous random variable. With the discrete random variable, on the other hand, each number is like an integer or something like this, generally, but it's discrete. So each value has a particular probability of occurrence. Okay, I would say. Okay, so that is the difference between continuous and discrete. Discrete, each number has a probability. Continuous, each interval has a probability. An interval can be any length, but it has to be an interval between, meaning between a number and another number. This is an interval. Okay. Okay. Here is an example of a continuous uniform random variable. Suppose NU students are waiting for the bus. Okay. The bus arrival time is set at 5 to 15 minutes from now and is distributed uniformly. The bus arrival time. Okay. Call bus arrival time random variable x. This means that the bus will not arrive before 5 minutes or after 15 minutes. It's going to arrive either between 5 to 15 minutes from now. Not after 1 minute, not after 2 minutes, for sure. But between 5 and 15 minutes. And not after 15 minutes. Okay, everybody? Okay, so this is an example of continuous uniform variable because the bus can arrive what? At 5 minutes and 5 seconds. It can arrive at 5 minutes and 50 seconds. Or it can arrive in 7 minutes and 10 seconds, right? It can arrive at any time. And the precise time of arrival is essentially probability of 0, a precise time, okay? So I can give you probabilities at intervals here, again, okay? Since it's uniformly distributed, this is saying, let's look at the questions and then we'll talk, okay? So the first question is, state the outcome space, the PDF, and provide a graph of the PDF. Okay. Well, the outcome space in the PDF, the outcome space is the interval from 5 to 15, like this. Total area or total probability, therefore has to sum to 1. So the PDF, therefore f of x is 1/10 for x between 5 and 15. And if x equals 0, right? Otherwise, so f of x is 0 here, 0, 1/10 between 5 and 15, and back down to 0 for the rest of the x's that are possible. Okay? Okay. And the graph looks something like this. Okay? Okay. Graph. The other solution. What is probability P between 5 and 9? This asks, what is the probability that the bus takes between 5 and 9 minutes to arrive? It's 0.4. How do I know it's 0.4? I just take the area 5 and 9 here. So the base is 4 units long. It's 9 minus 5. This is 4 times 1/10 is 0.4. So again, 4 times 0.1 is 0.4. In this case, 40% chance of arrival between 5 and 9 minutes. Again, assuming that it's a continuous random variable, okay? Okay. What is the probability that x equals 9? That is, what is probably the bus takes exactly 9 minutes to arrive? Well, exact times has to be 0 because no bus is going to arrive exactly at the exact time. It's either going to be, right, it's very, very small chance. Because there is infinite amount of times it can arrive. It can arrive at 9 minutes 5 seconds and 9 minutes 3 seconds. These are all different from 9, right? Okay. What is the probability x is between 1 and 2? It's 0 because it's indicated by the distribution the bus will not arrive before 5 minutes. Nor is the area between 1 and 2 is also 0. So I have here 1 and 2, the area here is going to be 0. There's no area there. Okay. Okay. So moving on, this was a continuous uniform random variable. Now we'll talk about another continuous random variable called the normal random variable. And this is another continuous distribution. Okay. The normal distribution is a bell-shaped distribution. It looks like this. Okay. The bell shape implies that values closer to the center are more likely than at the ends. So values close to here, where this mu is, are more likely than in the ends. Okay. And this has f of x on the y-axis, this probability here, which the continuous is for 1 unit interval. Remember the value here, if I get a value of like, I don't know, 0.3, that means, okay, if I get a value for 0.3, depending on my location x, roughly at the x where 0.3 is, right, if 0.3 is here, plus minus 1 unit from there, or half a unit from x, let's say the mean is I don't know, x maybe like 5 or something like this. Plus minus 0.5 from 5 will be around 0.3. Wherever x will be 0.3. Anyways, there is this mu here and the sigma. These are actually the mean and the standard deviation of this normal. And once I give you the numbers for these, the E is 2.7. Is this natural number. Okay. And then once I give you these values, then I specify x, and for each x I can get a different, I'll get a distribution that looks like this. Okay. Okay. So moving on. So the formula here is a little bit more complicated than the simple 1/8 or 1 over the base formula for the uniform distribution in this case. Okay. It's a little more complicated. Unlike the discrete random variables, most studied continuous random variables have well-known distributions. Okay. The general look of the distribution has a name, like the uniform or normal examples. The name alone, however, does not refer to an exact distribution. It reflects a family of distributions. And again, these are special distributions, special continuous distributions, because they have these families there. Okay. A distribution could still be called a uniform, for example, but have a different size outcome space or a different outcome space location, both of which produce different distributions and will have different PDFs. Okay. For example, in the first example, it was between 2 and 10, a uniform between 2 and 10. And between 2 and 10, the PDFs or f of x is what? 1/8, if you remember. In the second example with the bus waiting time, it was between 5 and 15, right? And what was the PDF there? Because the base is 10 units long, right? The height has to be 1/10. So f of x was 1/10, or that's what the PDF was, the equation of the PDF. Okay. So again, they're both called uniform distributions, but have different outcome space and different probabilities associated with 1 unit interval, let's say, on there. Okay. But what is their common theme is that equal intervals have equal probabilities. That's why it's called a uniform, for example. And this is why I call every distribution like that a uniform. It's flat. But this is the family of distributions. Exact distributions, you have to specify, in particular for uniform, specify the beginning and ending points. If you tell me the beginning, maybe like 2, and the final one 10, I can tell you, okay, it starts from 2 and ends at 10, it's uniform. That means the height is 1/8 because the base is 8 units long. Okay, so I need to specify beginning and ending points, and these are called parameters. Okay, so if you want to specify an exact uniform distribution, it requires specific knowledge of the outcome space, length, and location. Therefore, parameters are used to specify the exact distribution. Again, for uniform, this is 5 and 15, the beginning and ending points. Okay, in this case, for the uniform. However, the normal distribution is also defined by 2 parameters. Its mean, this is the location of where the bell-shaped curve is, or the maximum, kind of, and the variance, how spread out it is. This was where, you remember in the equation there was the sigma and the mu. The mu is the mean, and the sigma is the standard deviation, or the sigma squared, in this case, is the variance. It is how tight or fat the normal is. Okay? Okay? So, just one moment here. Okay. So, the normal has a possible outcome space from negative infinity to positive infinity. Therefore, specifying beginning and ending points of an outcome space does not make sense here, because the outcome space is infinite for normal. I cannot say it starts from 5 and ends on 10. Okay, but the main two parameters for normal that are widely accepted, you can say that has a mean of 5 and a variance of 16. So actually, if you specify the normal's mean and you specify its variance, it can give you an exact normal distribution. So I'll give you an example here. Here's a normal with the same variance, the same spread, or the same sigma, but different mu. Different mu. Okay, so this one, the first one has a mean of -10, and maybe a sigma of 1. Let's say sigma 1, mean of -10. Then if I plug in x in the equation, it spits out an f of x, and it plots something that will look like this. The second one has a mean of 0, and the third one has a mean of 25, like this. Okay, so again, same spread but different means in this case. Now this one has the same mean, maybe the mean is 10, let's say, I don't know, 0. Okay, maybe same mean, or the height is the same, the most likely numbers are the same, but this one is much tighter, has a smaller variance, a smaller standard deviation, and this is much bigger, higher variance or higher standard deviation. Okay, different sigmas here. Okay, so what are some properties of a normal? Its shape is symmetric. That is, when you cut it in half, the two pieces are mirror images of each other. Okay, so now we're continuing. Okay, so properties of normal distributions. The whole family. This is properties of the family. Okay. Its shape is symmetric. Again. Okay. Its distribution has a bump in the middle with tails going down the left and right. So the middle has the highest probabilities. The middle. That's what it's saying, okay? The mean and the median are the same and lie directly in the middle of the distribution, okay? Probabilities for a normal. It is difficult to compute probabilities for a normal distribution. You have to take areas under the curve. You can approximate them with straight lines. It's not a problem, okay? Area under the curve again represents probabilities, but it's difficult to compute since there is no straight lines. One way to compute is using calculus, the integral, but this is beyond the scope of this class. Other way is to look at tables. There are also properties based on standard deviations. I want you to know. So, all normal distributions have the following. From the mean of the normal, plus minus 1 standard deviation is 68.26% of the data. Plus minus 1 standard deviation. Plus minus 2 standard deviations is 95.44%, and plus minus 3 standard deviations is almost the entire distribution, 99.72%, or 0.9972 the area. The area here to here is 0.9972. Okay? And of course, that means the area here to here is 0.6826. Okay, everybody? Okay. Formal writing examples. For uniform on an interval AB, we can say that x, in this case, is a uniform from A to B, starting point A to finishing point B. The example was 5 and 15, if you remember. Okay. Now, for given random variable x, you can say it's normally distributed. If it's normally, you say x is normal, like this, with the mean mu and variance as the second parameter. So the first parameter is mean in this case. It's not the starting point, because this is negative infinity, all right? But the two parameters that are unknown that give you an exact, exact distribution are the mean and the variance. And when you specify the mean and the variance, you get an exact normal, right? Okay, and this is how you write it. A very special one is a normal 0, 1. It's called a standard normal, with a mean of 0 and variance of 1, and a standard deviation of 1 as well. Okay, is an exact distribution stating that the mean is 0 and variance is 1. This is known as standard normal. Okay, and basically, this is why is this distribution important, the standard normal? Well, I'll tell you why. Because generally, you don't know probabilities for normal distributions. You need tables. The trick is to use a table for normal 0, 1 and just do a transformation of that to any other normal. Okay? And once you do the transformation, you can get from any other normal to, you transform the any other normal to normal 0, 1, and you can use tables to give you probabilities. So you would, it's important because you have tables for this normal 0, 1, for this standard normal. So that's why it's important, okay? Okay, so moving on. Now we covered the basics of these random variables and how to know probabilities in them and so forth, okay? Let's move on to expected value and variance of a random variable. So what is this? Okay. These are different from the mean and variance that we computed when we have data. Remember in the chapter 3, the last class, in particular, we computed from data this mean and variance. Well, this is mean and variance of a distribution. Okay? So it's a little bit different. Expected value and of a discrete random variable. So the expected value is also known as the average or the mean. aka means also known as, the average of the mean. Given a random variable x and its distribution, it will be possible to calculate its expected value and variance. Okay? The expected value is a measure of location and is also known as the theoretical average or mean. It is pretty much the balancing point of the distribution. So I'll tell you what, if you put the distribution on some kind of a balancer, you put it there, and this is like the center of gravity will be there, okay? Is the center of gravity point, okay? So the whole distribution can balance on a scale, like a little, like a balancer, okay? And usually this is the center. For the normal, it's the center. For the uniform, it's also the middle, the center. But for other distributions that are skewed to the left or the right, it might not be the center. Okay. Formally, the expected value of x is abbreviated as EX, or the expected value of this random variable x, or mu. To compute for discrete random variable, multiply the particular outcome x by its probability f of x and sum over all. So the formula is expected value of x, like this, is a summation of x times f of x, or the individual outcome times its probability. You take all of those, you multiply them each other, and you sum them all up. And that is the expected value. Okay. What about a variance of a discrete random variable? And sometimes, of course, you can say variance of a probability distribution, or a variance of a distribution. So sometimes this is interchangeable, random variable and probability distribution. These words are interchangeable sometimes, okay? Anyways, the variance is a measure of spread of the distribution. The higher the variance, the more spread out the distribution is. The variance is roughly equal to the average squared distance from the mean, as in the sample variance definition. Remember, in chapter 3, we did the sample variance, where you have a whole bunch of data points, and we use the computer to compute them, but you can compute it by hand. This is the average squared distance from the mean, is what it was, how spread out the data is, right? In this case, this is how spread out the probability distribution is, this variance, okay? Anyway, formally the variance of x is generally abbreviated as v of x, or sigma squared, okay, like this. Formula for discrete distribution, the variance of x, sigma x. So if I know the exact distribution is discrete, I compute its mean first, that's mu, and then, and the formula for that is above the previous slide, right? Then I subtract each observation, each possible outcome, let's say non-observation, each possible outcome from mu. I square that and I multiply by its corresponding probability, and I add all of them up. Add all of them up, okay? Again, x represents each possible value of the outcome space, and f of x is the probability, mu is expected value, okay? Okay. The standard deviation is again just a square root of the variance. The square root of the variance is the same as before, okay? What about expected value and variances of continuous distributions? These were discrete, they had formulas. For continuous distributions, it's a little bit more tricky. The formulas discussed can be used to compute expected value and variances for discrete, it can be tricky and generally requires calculus, if you want to know. The good news is that continuous distributions are well studied, and the spatial distributions have formulas for expected value and variances. And these formulas are based on the parameters, right? To give you an exact distribution, you need parameters. So you plug in the parameters, and the formulas will spit out expected value and variances, okay? In particular, for the normal distribution, the parameters are expected value and variance, So this is very easy. For the normal, you just look at the parameters and they're the expected value in your variance. Okay. The expected value of the uniform is just that center. Okay. The variance of the uniform is the ending point minus the starting point, or the difference between the two, right? Or how long the base is, squared divided by 12, where B and A are the parameters of the uniform, the beginning and ending points, right? Let's see the next one. The expected value of other continuous random variables is the balancing point. Its standard deviation is also approximated by average distance from the mean. You can approximate this. Okay. Final remark here. It is very important. Do not confuse expected value of a distribution with expected value of a sample, or simply a list of numbers from the data. Same goes for variance. There's no numbers here. I've not taken any samples. I don't have realizations from a random variable, okay? And I don't have a list of numbers. So to do the expected value calculations, with the die roll example, I have not actually rolled any die to compute expected value or mean. Okay? So again, this is expected value and variance for a probability distribution. It's not for data like it was in chapter 3. Okay. Now, what is the relationship between data and, in this case, a probability distribution? I'll tell you what. If you have a die and you know its probability distribution, if it's a fair die, okay, if I roll the die, let's say I compute, if it's a fair die, then I know its probability distribution. I can compute its expected value and its variance of the theoretical probability distribution. In this case, the random variable also. Okay. And those numbers, I'll get something like 3.5 for the mean, and the variance will be roughly about 1.5 probably, or the variance squared will be around 3. The standard deviation will be 1.5 for this probability distribution. Okay. Okay. For the die roll random variable. Okay. This, I'll tell you the link between getting actual data. If when you roll the die, you'll get a whole bunch of numbers. This will be like your sample. Okay. And this will be like numbers like 1, 2, 5, 6, 3, 5, 1. Okay. You'll get a whole bunch of numbers. If you roll this a large number of times, like 1,000,000 times, this die, okay? And based on the sample, you compute the mean and you compute the variance of the sample data from the die roll. Those numbers will be almost exactly the same as the numbers on the probability distribution. 3.5 for the mean, and the variance probably 1.5 about. I don't know, I have to compute it, okay? It will be almost exactly the same as the mean and variance of the distribution. So as your sample size gets big, if it goes to infinity, then in that sample, the variance and the mean of that sample will be exactly the same as the variance and the mean of the probability distribution of the die roll. Okay, you call this the sample mean converges in probability to, in this case, the probability distribution mean. And okay, and then the sample variance converges in probability to the random variable variance, or the probability distribution variance of the die roll. Okay, this is just something to consider, that the bigger the sample I take from these distributions in a case, the sample mean and variance will approximate the distribution mean and variance, okay, as they get bigger. Okay. So this is the link. And lastly, this is like a final word here. Random variables are important in inferential statistics. The population, as we call them in the introduction, can be seen as a random variable with an unknown probability distribution. To obtain an inference about the population, that is trying to infer the population random variable as mean or variance, perhaps, or some kind of other characteristic, one takes a random sample or realizations from population. We will discuss this in inferential statistics chapter. Okay. So the important thing to remember is the population random variable can be treated like a random variable. Okay. It's used for inferential statistics. Anyways, let's look at some questions now. Suppose that one side of a 6-sided die is a bit heavier, so that the probability of landing on 6 is 0.5, and the other numbers are equally likely. Let the random variable x represent this die roll. If I roll the die, what is the probability of getting above a 3? Above a 3, so getting 4, 5, or 6. Provide a table and a graph, the outcome space, and its associated probability mass function. Hint, the probabilities have to add to 1. So getting above a 3 means I need to get a 3, 4, 5, 4, 5, or 6. Now, if landing on 6 is 0.5 probability, so it's a half a chance that I land on 6, and half a chance that I land on any of the other numbers, okay? The other numbers will have to, and they're equally likely, they'll have to have a 0.1 probability there, because there's 5 of them. And they have to add up to the other half a chance, right? Land on 6, and the other half will be the other numbers. So each one will have to be 0.1 probability, okay? So getting above a 3 will be 4, we have a 0.1 probability, 5 will have a 0.1 probability, and 6 will have a 0.5 probability. So getting above a 3 will be 0.7. 0.7 probability, okay? And watch, I drew it here. Notice if I add all of those, 0.1 plus 0.1 plus 0.1, so 0.1 times 5 is 0.5, plus 0.5 is 1, right? This PMF has to sum to 1, okay? And getting above a 3, in this case getting a 4, 5, and 6, or 6, either happen if it lands on 4, lands on 5, or lands on 6, this is a 0.7 chance of occurrence, 0.7 probability, okay? Okay. Question 2. Expected value and variance of unfair die roll. Again, consider the unfair die roll. Compute its expected value and variance. Okay. Okay. And standard deviation. Okay. Well, consider the unfair die roll. Again, what is the expected value and variance? Well, here I already computed it, so it's 4.5 expected value, and my variance is 3.25. This is how spread out the distribution is. Again, what does it mean to have an expected value? Now, the variance is average squared distance from the mean. It's a little bit more tricky. But this means if I put a little balancing beam here, the whole thing is going to balance. If you put it on a table, right? You put it, imagine these points here that connected somehow by tiny rods that are weightless, in a sense, okay? So this weighs the most. Okay, it's a 0.5 weight here. Okay, this is like a 0.1 weight. If I put a little balancing beam here, around the 4.5, I'm guessing, or it's not going to be 3.5. If it's 3.5 in the middle, this is going to fall to the right. So a balancing beam should be around 4.5. It's like that center of gravity. Okay? Okay, everybody? And then the answer is 4.5. How did you compute it? If you don't want to think about this, you add 0.1 times 1, because it can be a 1. Then the probability of getting a 2 will be 0.1 times 2 plus dot 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 dot. You continue on 0.1 times 5 plus 0.1, not 0.1, 0.5 times 6. So I multiply each one of the possible outcomes times the probability. Okay? Okay. Okay? If you do the math, that should equal to 4.5. Okay? What about the variance? Okay? How would you compute it? For the first outcome, which is 1, 2, okay? What is this going to be? Well, it's how you do it. 1 minus 4.5 squared let's if you want, we can use the equation tools so it's easier to see here. Okay, okay, do it like this. 1 minus 4.5 squared times 0.1. 0.1 is the corresponding probability on the first, if it's the first outcome, it's the corresponding on the first outcome. Okay, like this. Okay, times, yeah, you could say 0.1 times the other one, and it doesn't matter. Okay. 2 is the second outcome. 4.5 times the second outcome plus dot dot dot. And now what is the third? Let's say the last one. 6 minus 4.5 squared times 0.5, because it's the highest probability. Okay, like this. Then I computed it already. You can double check this, okay, with a calculator. It should be 3.25. And this 1.8 is just the square root of 3.25, okay? Okay. More questions here. Consider a uniform distribution, again, from 5 to 15. What is the expected value? This is just the middle, so it's 10. What is the variance? Use the formula b minus a squared. So 15 minus 5 is 10 squared. 100 divided by 12, 8.3. Standard deviation is just the square root of 8.3, 2.99. Okay. Consider a uniform between 1 and 10. What is the PDF? The PDF equation for uniform is f of x over 1 divided by b minus a. So 1 over 9 for x between 1 and 10 and 0 otherwise. So it's 1 over the base. The base here is between 1 and 10, so it's a length of 9. And 1 over 9 for x, okay? What is the probability of getting a value between 1 and 2? Well, they're 1 unit apart, so it's 1/9. 3 and 4, the same. What is, that's another one. What is the probability of getting a value between 1 and 1.5. Again, this is uniform, equal probabilities and equal intervals. This is the trick. So guess what? It's going to be what? Not 1/9, 1/18. Even smaller. Half as small, right, as before. Okay. So you're getting this, right? Okay, okay. Consider a normal distribution. X, 0, 1. So this is a standard normal. A mean of 0. So the mean and the variance is 1. The standard deviation is also 1. Okay. Consider X normal 7/16. The expected value is 7. The variance is 16. The standard deviation is 4. So plus minus 4 units from 7. How is this distribution going to look like? 7/16. I'll show you. You see here 4. This will be here 7. It will be centered at 7. And plus minus 4 will be the points here. So this will be 11. And this will be 3. And the majority of the distribution will be here between 3 and 11. With a highly probable around the 7 area. That's how it's going to look like. Okay. Okay. I have a few slides open. It's okay. They're the same stuff. The same stuff. It's okay. Okay. Lastly, a question for class. Okay, you guys told me the other day you want some questions to be answered during class. So this is a question for class. We'll talk about it in class. Okay, in the discussion. Suppose that NU, before the quarantine, there is a salad bar. This is where a server grabs salad and puts it on a plate for you. The amount of salad grab X is a continuous random variable that is distributed like a right triangle. This is also known as a triangular distribution, between 70 and 100 grams maximum. This is the max that will fit on the spoon. So basically, the highest probability is on the 100 grams. So basically, I go to the story is the following. I go and get some lunch or something like this. And whoever is serving the food, the server asked me, would you like some salad? And then I said, okay. But he grabs with a spoon and he puts salad on my plate. A full spoon, the maximum that the spoon can fill is 100 grams of salad. Okay. The minimum it can fill is 70. So actually, when he fills the spoon and gives me the salad, it will be between 70 and 100 grams. I know this for a fact, between 70 and 100. But more likely than not, he'll always scoop somewhere pretty close to 100, a lot closer to 100 than closer to 70. Because it's a triangular distribution, if you see here, the area, let's say between 90 and 100, is much bigger than between 70 and 80. So I'm more likely to get between 90 and 100 than 70 or 80, than between 70 and 80. Okay? So more likely or not, he'll make a full scoop or close to a full scoop of salad. And sometimes he'll give me a little bit less. But more likely than not, it will be closer to a full scoop than closer to let's say a scoop with 70 grams of salad, okay, or a more empty scoop, okay. Okay, so here are my questions, and you guys please let me know the answers if you can, okay. During class we'll talk about it. What is the maximum height of the distribution? This is the vertical height at the 100 grams. Hint, use the fact that the area of the triangle is equal to 1, and the area is also equal to base times height. So I know the base, right? Base times height divided by 2. So I know the total area is 1. I know 2, and I know the base. I just solve for the height. In this case, I'm talking about the height here, between here and here. So what is this question mark? It corresponds to the height, okay? The first question. Once you figure out that question mark, what is the probability that the server will put exactly 100 grams on the plate? Exactly 100 grams. What is the probability that he will put between 90 and 100 grams? What about between 50 and 60 grams? What about between another one, between 70 and 80 grams? Okay. Okay. What is the average amount that the server will put? Hint, this is the balancing point in the distribution. You can look up triangular distribution on Wikipedia for the formulas, because again, it's a family of distributions. It's called the triangular one, or the triangle one. And this family has parameters, and once you get the parameters, it'll spit out expected value and variance for you, okay? But guess what? Because what you're doing now is, imagine you're trying to balance a triangle. It's going to be somewhere here. I think somewhere closer to 100 than 70 for sure to balance it. I think it's going to be around 90, 88, maybe 90, okay? It will make sense. 70 is here, 80 is here, 90 is here, right? So 90 is reasonable, I would say. Around 90 is my guess, okay? Balancing point. Okay, everybody? So this is it for today's class. Look at your slides, and let's meet on Wednesday and we'll talk about this. Okay, bye-bye.